Sorry for the technical difficulty there. I think we're back in recording. Okay, so today we have the 17th lecture for wireless without batteries, and today we're going to be talking about piezoelectrics and surface acoustic wave devices. This is kind of a nice change in pace. We do a little materials today, and then we talk about how those materials are used for sensing in batteryless sensors. It's kind of an interesting technique. So we'll have a test in this class. Yeah, what is that? 12 days from today, the Monday. And that'll open up the testing window for the distance learning students. Again, I'm finding I'm having about a 1 to 2 day extra lag time in uploading videos because of just export bandwidth issues here from China, I think. So apologies if the videos show up a little late. I'm working on them. I managed to upload Monday's video just this morning, and I just need to go into T-Square in the Cultura site and publish it, which is its own nightmare, but the hard part's over at least. Hopefully y'all distance learning students, if you haven't already done it, go ahead and send me which project that you've decided to work for the project in this class. That will be due April the 24th. So now let's talk about piezoelectrics and SAW devices. First, piezoelectrics are an interesting topic to study, even in the absence of transferring information and doing wireless sensing, simply because they're an interesting energy harvesting technology, converting vibrations into electrical energy, and an interesting sensing technology of themselves. Ones that we don't really talk about much in electrical engineering. You know, I never had a course growing up on piezoelectrics, but it's an important part of technology nowadays. And you can do some really interesting things at RF with piezoelectrics, especially involving surfaced acoustic wave filters and now bulk acoustic wave filters. We'll talk about the difference and why that's important. But first we have to understand the piezoelectric effect. Now, y'all took at some point a solid state electronics course, right? It taught you all of the devices that we make, whether it's metal, ceramic, semiconductor, all these types of materials. If they are not amorphous, they have a crystalline structure to them. They have this basic unit of repeating structure that defines their structure. So for example, table salt, if you look at it under the microscope, it's a bunch of alternating molecules of sodium and chlorine. So if I looked at it in 3 dimensions, the unit cell that I would use to replicate this is a simple cube. I have sodiums and chlorine atoms alternating all along the edges of my cube. So we call this a simple cubic structure, and you can see that if I basically take that unit and replicated it up and down and over and around, I get all of the crystalline structure of salt, right? Now, there are lots of different shapes that describe the crystalline structure of things, right? There's face-centered cubic, body-centered cubic. You know, you can put stuff in the middle and still have a replicatable structure. You can put stuff on the faces. Hexagonal. There's all these different shapes that we know lead to crystal filling in three-dimensional space. This particular shape, this simple cubic, and most of the shapes that we're aware of, have something called an inversion center. That is, I can pick a center and I can invert the shape and I get the same shape out of it, right? If I take I would put like a three-way mirror in the middle of this shape, I would still see a cube. So we call that an inversion center. Now there are some shapes that do not have inversion centers. One of the classic ones is quartz or silicon dioxide. This is SiO2. Quartz has a tetrahedral structure, and it looks like this. There's a silicon in the middle, oxygen off to the sides here, and the oxygen points form the vertices of a tetrahedron. And the thing is, unlike the cubic center, this does not have a center of inversion. Because if you go in and say, okay, right here, I'm going to start at silicon, I'm going to invert the thing, what you get is an upside down tetrahedron. You do not get the original shape, you get the upside down tetrahedron. And interestingly, that makes a big difference in the material properties of something. Why is that? Well, if you remember from your chemistry, you know that Si in this arrangement basically is an electropositive, it's a donor of electrons. Because it wants to be positive. It easily gives up the electrons. So the electrons will spend less time at the silicon and more time with the oxygen, which are very electronegative. Now, in this form, I've got charges that have migrated more towards the oxygens than the silicons. No net charge has changed, though. This is still a charge neutral unit, and it has to be because this is what's going to replicate throughout the entire crystalline structure to form the material. So I don't have any net charge. However, in this state, I have charge symmetry. So if I do like a Gauss's law, I don't get any net flux out of the unit. And I get a fairly minimal dipole moment out of here. You'll get some E fields probably that go from positive to negative. They'll point in this direction, but they're relatively minor. And confined to within the atom. Until you force a mechanical deformation onto the atom. So if now I have some pressure now, imagine I'm putting some pressure on this quartz substance, which means, let's say it's coming from down, so I'm pushing down on all of the atoms. And I'm getting a mechanical transfer of force. Well, what this is going to do is it will impart a slight bowing to the crystalline structure. Very small, almost imperceptible. But now, I no longer have the ideal charge balance that I had. So, force is coming down. These kind of swing out just a little bit, just a tiny bit. And maybe this force is down here, so it's a little bit closer. And what happens is that now I have a very slight dipole moment from here to here. almost hard to measure. However, keep in mind, if I have even a small amount of material, there are billions of these units stacked up on top of each other. And so the end result is that a mechanical deformation will produce a voltage across there, a measurable voltage. If I have a hunk of material and I put enough force on it, I can measure a couple of volts coming out of that. I can't drive a lot of current with that. This is a very high impedance source, right? I'm just adding an electrostatic dipole moment that will quickly extinguish itself as soon as I hook something in a circuit to it. But it's interesting that I press it down and I get a voltage coming out of it. And what's more, I can do the opposite. I can stretch it. If I instead reverse the force and stretch it, I will get the opposite polarity. Those oxygen atoms will swing down a little bit, impart a negative dipole moment to the other side of the molecule, or the other side of this crystalline unit, and I will get the opposite effect. And the other really neat thing about piezoelectrics is that it is a reversible phenomenon. So I've presented it here as if I'm pressing it in one dimension and I'm getting a voltage that comes out. You can actually do the opposite. You can impress a voltage and it will deform slightly. If I change the polarity of that DC voltage that I've attached to it, it will deform the other way. It will stretch out a little. So quartz is one of the most common examples, one of the most abundant materials on the face of the earth, so we have plenty of it to make. And this is a great way to, great material, first of all, to make an oscillator out of. We've talked about oscillators in this class. So if you take a little piece of quartz like that and put it in a circuit, and it's a very specified dimension, then it will have a Q factor. And if you hit it with a step or an impulse of electricity, you'll actually excite a wave through it, and that wave will ring, and the remaining tone left will be a very high Q mechanical tone that you can measure electrically. So a quartz oscillator is a timekeeping piece that can usually make a very stable frequency source, somewhere around 10 or 20 or 40 or 30 megahertz, somewhere in that range. If you want the resonance to go higher, you got to have more of the material. And that most quartz oscillators that are fairly stable are in that lower megahertz regime, just because of the size of the device that you have to make. And so that's good. That's actually that's one of the most impressive inventions in electronics that has probably never been noticed, right? All of a sudden at the end of the 70s, 1970s and early 80s, people started wearing wristwatches. Why was that possible? Well, because we finally had accurate timekeeping. Up until that point, almost everything in terms of timekeeping had to be done mechanically. Clocks with pendulums, that sort of things. And it's very unwieldy to make a portable device that behaves in such a way. In fact, there was I have to look up the story, but for the longest time in ship navigation, when people started to circumnavigate the globe and to go to far off places, it was always very easy to measure your latitude, right? You just look at the North Star and you measure with a sextant or protractor or whatever you've got a hold of, and try to figure out what that angle is, and you know what your latitude is. However, it was a nightmare to measure longitude because you're always moving, and you never know exactly when to make your longitudinal measurement unless you had a really, really accurate clock. And so I remember there was this challenge to the Royal Navy that the Queen of England issued at one point, maybe in the 1800s or maybe a little earlier than that, I can't recall, but it was a challenge to figure out the longitude problem. And to do that, you basically had to make a very accurate clock, something that was accurate to, at least a fraction of a minute or several seconds. so that you could do those star measurements, note the time, and then back solve exactly what your location was. And the winner of the challenge was this clockmaker who made this beautiful pendulum, and I think he made most of the components out of wood, because one of the problems is you got to take it to sea, and if it's made out of metal, it rusts very quickly. And rust, turns out, introduces a very interesting time variation to clocks. So, you know, there's this whole book written on the subject. It's really fascinating. But anyway, it's a very big deal to be able to measure time accurately. And as electrical engineers, that's like the one thing that we measure very precisely, time. We almost measure it to a limitless degree of precision nowadays with our atomic clocks and ultra-disciplined oscillators. So I even have a colleague at Georgia Tech. He's working on how to put an atomic clock on a chip. You know, that'd be really cool. So being able to, yeah. And the thing is, you take it for granted that, oh yeah, I got a watch. Of course, it keeps us at the right time. I mean, before that, it's interesting to think that our electronics didn't work good enough all the way up until the 70s to do something like that. You'd lose a minute every day because the oscillator was not disciplined. And darn it, after a couple of weeks, you were a half an hour behind everybody else. And it was frustrating. You kept having to redo your clock. So anyway, quartz winds up being a great thing to make a disciplined oscillator out of. And you don't think of it, but you're actually using mechanical vibrations. In a way, it's a mechanical pendulum all over again. But you're using the piezoelectric vibrations of this interesting material that transduces mechanical vibrations to voltages and vice versa. And quartz is not the only piezoelectric material, although it's one of the most popular because it's fairly temperature compensated. Because we're dealing with mechanical properties tend to vary as a function of temperature. And this becomes a problem for timekeeping because you've done all this work to make this really nice timekeeping standard, and then all of a sudden you go out in the cold, on a cold, snowy Shenzhen day, and now you're 10% off of your original estimate. But it turns out that the coefficient of friction, of expansion, and some of the mechanical properties of quartz is relatively flat at room temperature. So that's another reason why you see it used so much. However, there's also other forms of piezoelectric. So for example, there are some ceramic structures that have a cubic-like or bicubic type of symmetry, like this, for example. And I'm thinking of one example of this is lithium niobate. And niobate refers to this kind of ceramic structure. And then it happens that every other plane, there's a little positive lithium ion right here, Li, in the middle. And the thing is, it's never exactly in the middle, right? If the substrate is hot, if this substance is hot, then on average, the lithium ion is in the middle. And of course, it's a positive ion, and there's a little bit of negative over here on all these guys to compensate it. Again, charge neutral unit, and there's this positive lithium ion in the middle. And if it's really hot, it's got a lot of kinetic energy, and quantum mechanically, it spends 50% of the time in a little bit above the center plane and a little bit below the center plane. At room temperature, however, it tends to go to one side and stay there. There's not enough kinetic energy to push it over to the next side. So what that means is that if you look at it from the side, there'll be one, I'm going to draw it exaggerated, but there'll be a Li up here, and then 50% of these units will have an Li down here, and so forth. Again, charge neutral, this doesn't matter. However, if you poll the device, that is, you take this material, you heat it up, the LIs are kind of bouncing back and forth, you don't know which side they're going to end up, but you apply an electric field and then you cool it down. Well, the electric field will push all of them mostly to one side while they are hot, And then when they cool down, they all stay on the same side. And so what this will do is create it will break the inversion symmetry on average for this repeating unit. And now if you compress the device, the substrate, you'll get that same electric dipole moment that's proportional to force and accumulates through the medium. In fact, this is a phenomenon that can happen unintentionally in a lot of devices, this pulling of ceramics. My students are always complaining about this. They make ceramic capacitors, where they basically, you've got a really nice insulating ceramic between two plates, and you can use this at microwave to make these really small capacitors at RF frequencies. And it turns out that the capacitors sometimes have time-varying properties. So you put it in, it was an 8 picofarad capacitor when you started out with, and it might only be a 3 picofarad capacitor by the end of the lifetime of the piece of electronics. That's probably a little exaggerated, but it's because of this polling phenomenon. Over time, the ceramic material that they use to make these microwave capacitors poles, and it actually changes the capacitance of the material. It's kind of interesting. Yeah?
This is a fluoride or chloride or BR?
BR?
Oh, sorry, it's fluoride at LIF or LICL or?
So when what I've sketched here is kind of a ceramic called lithium niobate. I don't know what the other, I have to look up on my notes what the surrounding atoms are, but it's a positive, electropositive lithium atom in the middle. And there are a lot of different variations of compounds that exhibit this behavior. Maybe they have bromine or fluorine. I'm not familiar with those though. So okay, what is all this good for? So what? Now you have something that makes a small voltage as a function of pressure or force, or vice versa. So what you have to do now is imagine all these atoms in your piezoelectric structure in a material. And what happens when that material starts to vibrate? Well, there are two interesting wave modes that we talk about when we vibrate materials. One is the bulk acoustic wave, and the other one is the surface acoustic wave, SAW and BAW. The bulk acoustic wave, of course, you bang this on top and then you launch a wave where the mechanical displacement of the atoms in the material travel down and they can reflect off of interfaces and the like. And the surface acoustic wave is a slightly different wave. This is where you create a vibration and launch it from the side, and these ions or these atoms vibrate back and forth and cause their neighbor to vibrate back and forth and cause this neighbor to vibrate back and forth. But by and large, this wave travels just upon the surface. And it stays relatively collimated, which means if I look at this from above and I launch a wave from the end, it travels at uniform velocity, and it doesn't bend or disperse very easily through the material. So, this suggests we can make a SAW transducer in the following way. If I want to convert electrical to magnetic or to mechanical energy and launch a surface acoustic wave, what I do, here's my piezoelectric material. And then I make an interdigitated transducer, where, so what I'm drawing here is going to be metal. And this will all be connected to one polarity. And then on the other side, I'll have another set of interdigitated fingers. Inter, of course, means between. Digitated means fingered. So these look like two metal fingers that are intertwined with one another. And then I connect this up here. And if I hook that up to an AC source, then what happens, if I blow this up and look at just one finger and then the finger next to it, I will have a voltage drop on the upswing that makes the E field point from here to here, from one finger to the next. And of course, that will mean that I've got I'm going to make a piezoelectric contraction in that direction, right? And then when I reverse the polarity, it's going to make an expansion. And so if I oscillate back and forth at a particular frequency, then I will wobble the piezoelectric back and forth. And if I happen to do this so that if I make this transducer so that this is basically lambda over 2 apart, then by the time I reverse polarity, the bottom half of my phase will have propagated into there, and I'll basically get constructive reinforcement of my transduction. So this interdigitated transducer, because it's also alternating positive, negative, if the digits are this magical half wavelength apart, I will mechanically reinforce the surface acoustic wave that I'm forming when I transduce power into this medium. And I will launch a nice, strong mechanical wave down my object. Now this is kind of perplexing, right? Because you think of waves in terms of like sound waves. What do sound waves typically oscillate at? What are the frequencies? Down in the lower kilohertz, right? Are there RF oscillations? Does the air RF? I mean, we work in ultrasonics, and that's when the frequency goes up to megahertz. You can't hear that. What if we went up to 915 megahertz or 2.4 gigahertz? Can we transduce? Are there even sound waves, mechanical vibrations that high? Well, it turns out there are. I mean, there's no way you can hear them, and you can't feel them because they're operating at a time scale that you just can't sense. But these materials will have vibrational modes up there, and that's what you're exciting when you hit it with RF power. Now it turns out once you get above 6 gigahertz, it's really hard to make a surface acoustic wave sensor in this fashion. Yes.
How say the two parts of the gratings, should they have the same gap?
Yes.
But if they're the same gap, because one is charged positive, the
Mhm.
other is negative, and there will be like one positive between two negatives, and one negative between two positives. If they are exactly the same distance, will they have a balance of the force? Then it cannot vibrate.
So let's see, let me draw three fingers together. So this one, let's say this one is positive, and this one is negative.
If they are
So in this finger, one of these areas will experience a contraction, and the other one will experience an expansion, right? This material will bend out,
on both extremes.
and this will, and that, of course I'm looking down on the surface of my material in this diagram. These interdigitated metal fingers are on top of the material, like this.
You mean that it's not on the same plane? One
Well,
is-
it's resting on top, that's right.
Oh, okay, I see. Okay, thank you.
So if I look at it from the side, here's my piezoelectric material. And if I could look at it on the side, I'd see these little fingers resting on top. So I get expansion here, or say contraction here, expansion here. That's on the upside of a sine wave. On the downswing of the sine wave, then I get expansion over here and contraction over here. But of course, if this is half a wavelength in medium, then this vibration has transferred over here. This, what used to be a contraction, will have transferred over here and will now be reinforcing this, and will continue onward and get launched on both sides of the transducer. So here's the key thing. This is the magic of a surface acoustic wave or any type of piezoelectric material being used at RF frequencies. Your velocity of propagation in free space for a radio wave is what? Well, it's c, right? 3 times 10 to the 8th meters per second. The velocity of propagation inside an acoustic medium, because now we're transducing electromagnetic waves to acoustic waves, still satisfies the same principles. Lambda times frequency will be equal to the velocity of propagation. Everything's the same frequency. There's no discontinuity in frequency. So what has to give? The wavelength in the material shrinks down considerably because acoustic waves travel much slower than electromagnetic waves. How much slower? Usually about at least 4 to 5 orders of magnitude slower. And that's important because electromagnetically, if I want to make a device that has a resonance, I need to make it electromagnetically significant so there's enough time to vibrate around and make phase delays. That's hard to do in a small object because things are traveling at the speed of light. However, if you can slow things down by a factor of 10,000, then in a very small space, acoustically, I can do things like filters and resonance structures that would take up entire rooms, entire buildings, electromagnetically. And so I think we're past the recess point, but I will go ahead and explain a little bit more about that when we come back. We'll take a 10-minute break and I'll be back. Okay, we're back. Sorry for the break there. I think I took 15 minutes instead of 10, but I wanted to look something up for you. First of all, the chemical formula for lithium niobate. Lithium niobium, and oxygen. No chlorines or fluorines, but there are plenty of ceramics that have those, and I have no doubt that there would be some good piezoelectrics from those materials, since fluorine and chlorine have such electronegative, electron-greedy properties. They're always trying to snarf everybody's electron away from them. And the person that effectively won the longitudinal challenge was John Harrison. Actually started working on it, making maritime clocks in 1730s, but he wasn't really awarded a prize until about 1773. And I don't even know if it was the official prize. The longitude prize was actually announced in 1714. So it took quite a long time before you could even think about solving this problem. It was a little over 200 years ago. It wasn't that long ago. Anyway, points of trivia that came up in the previous 40 minutes that I thought I'd put to rest so that you could sleep well tonight. Now, what we were talking about before we broke was the difference in velocity of propagation between a surface acoustic wave and an electromagnetic wave. And this is one of the great success stories of electrical engineering. This principle of a surface acoustic wave device is one of the reasons why your phones are so small, your radio phones, because you can use this property to make filters. So what we can do, say we got our interdigitated transducer. And interestingly, the bandwidth of this device is basically going to be equal to the center frequency divided by the number of fingers. So it's interesting, the more fingers you have, generally the more efficient the transduction is, either to or from the medium. However, one of the problems is that the more fingers you have, the more narrowband the device tends to be. Okay. Now, say you launch a wave. You can also put things on this device, such as a piece of metal just riding on top, that acts effectively like an electric short. And this will also interrupt the mechanical wave as well, because, of course, the electrical and the mechanical properties are coupled in an acoustic wave, in an acoustic piezoelectric medium. And so these often serve as reflector bars. And you can put any number of these with various spacings along here. And if I were to model this electrically, what this would look like is a source with an impedance connected to a transmission line. And then every so often, I have a mismatch. I could represent that as a resistive mismatch between different segments. It causes various time domain reflections at the junction. So interestingly, this gives me the ability to synthesize a filter, something that has very sharp frequency response. And one of the things that has made your phone so small and so effective and work at all these different frequencies without being a pincushion of antennas, different types of antennas, is that, for example, you have something called a diplexer in your phone. It's a device that separates out frequency. So let's say you have an antenna in your device, and you would like to have a frequency that would break out, let's say, 860 megahertz and 920 megahertz, or 930 megahertz. This would be your European frequency allocation. This would be a North American frequency allocation, very close to one another. Or maybe instead of 930, you were doing LTE band, which is somewhere around 700 megahertz. And this is over a fairly limited band. You would like to have a device that would be able to filter out everything outside of those bands and then route 100% of that information down one path and another 100% of an information down another path. And this all before you mix down to LO to give you the proper dynamic range for your RF front end. Well, one of the ways they do that is with surface acoustic waves. Well, on the one hand, these surface acoustic wave devices tend to be a little lossy. Like, you don't get very good transduction. If you get more than a few percentage points of the power into this surface acoustic medium, then you're doing pretty good. On the other hand, you can build filters that are very small, and if you just put an amplifier on them, you can make up for the lost power. So this is how you get a very high Q filter at RF in a tiny, small space inside your phone. You excite with a transducer on one section of your surface acoustic wave medium. You put little reflector bars in there and synthesize the filter characteristic that you want. And that gives this a very nice frequency selectivity that then allows you to make sharp filter points for different frequencies. What's interesting here is that we can turn that around, and for the purposes of our class, we can now make a very useful sensing technology out of this if we wanted to. So let's say we've got an antenna, and here's our surface acoustic wave. Tag. Got the transducer up here, and then reflector bars. Well, these reflector bars may be fractions of a millimeter apart from one another on the medium. Electromagnetically, that's insignificant. Acoustically, that could be several wavelengths or more. And what's nice is that when the wave comes down and reflects back over the course of several millimeters, it will have traveled a very long amount of time in the electromagnetics world, right? And in doing so, if you put these bars in the right spot, you can sense these reflections, and these reflections can encode information, such as identification information. Think of each positional bar as kind of like a bit. If you take one away, it's like making a zero. If you put one in, you see the reflection on the output. And so you can grab information off of the SAW device without even having a chip that you need to power up and pull bits off of. Of course, the drawback is that it has to be hardwired into the piezoelectric medium. In fact, I've seen people use these for temperature sensing as well. If you use lithium niobate, which actually does have a thermal coefficient of expansion that's fairly sensitive at room temperature, the shorting bars get farther apart from one another. Not that much, but enough to measure it. And because such a small difference in the mechanical world translates into such a large electrical distance, when the wave is transduced into and then out of the SAW tag, you can actually look and measure the distance between reflections and gauge what the temperature of this device is. So if you want to make a jet aircraft engine turbine monitoring device, you want to monitor the speed and temperature of a turbine, say in a jet. Well, you can just embed one of these surface acoustic wave materials, hit it with RF, measure the Doppler shift, and then look at the time delay between different reflector bars on the material. You can guess what the temperature is. Those are the types of things people use these tags on. SAW filters and devices were actually used in spacecraft. I think the Voyager spacecraft, the one that was launched all the way back in the 70s, uses SAW devices because they're resilient, they're radiation hardened in space, and there's nothing to them. Put them in the ice cold reaches of space or the hot orbit around the sun, and they still work fine. Now, what makes this such a neat idea is that you're using the idea of slow acoustic propagation versus fast electromagnetic propagation. You could interrogate this type of device with something very similar to a backscatter reader. There's no load modulation, so it's a static system, but it's still relatively easy to de-embed from the environment. So what do I mean by that? Well, let's say you had a network analyzer and you were making an S11 measurement by connecting the port to an antenna, port 1 to an antenna. Well, here you've made a very simple and relatively sensitive backscatter receiver. The only thing is you're only going to measure backscatter, static backscatter. Like you'll send waves back out, and some of those waves will come back in with different time delays. And as a result, you're going to get an S11 that has a complex change in phase and amplitude, and it's going to be frequency selective as you sweep in frequency. And that frequency selectivity we measure with something called the coherence bandwidth. That is, what is the bandwidth over which this channel appears to be flat? And this is a strong function. That coherence bandwidth is really a direct function of how dispersive the channel is. By dispersive, I mean how many echoes are in the channel. So if you look at a radio channel, if you measure it in the time domain, just Fourier transform your complex S11 measurement, what you usually see is something that looks like this, a bunch of impulse responses, a little smoothed over in time. So it might look like this on the scope. But trailing off, that first energy that you see in the delay domain is your first return, which is usually also your strongest return because it's traveled the least amount of distance. It hits your antenna, it travels back, it hits your antenna, you see a big spike. But you see all the other scatterers too. Reflections off the window, off of the table, off of Dylan. And of course, these two measurements should be Fourier transform pairs, right? My S11 and then my power delay profile, or my was really a channel impulse response. Power delay profile is usually time average magnitude squared of the impulse response. And so that at the end of the day, the width, the RMS delay spread or width, we call tau RMS, how wide this thing is on normal, is inversely proportional to how frequency selective the channel is. The coherence bandwidth and the RMS delay spread are inversely proportional. As I get more dispersive in time, my frequency nulls and humps get closer and closer together in the spectral domain, and vice versa. My coherence bandwidth drops as tau gets bigger. As tau shrinks, I stretch out the peaks and the nulls, and my coherence bandwidth gets larger. The problem with making measurements in this fashion, looking at backscatter of the general environment, is I would like to have a tag. I've seen people work on this. They call it chipless RFID. So they put a piece of plastic or a paper and they put a pattern on it, a metal pattern, a unique metal pattern. You know, maybe bars of metal that represent ones and zeros. And every pattern will have a unique scattering signature to it with a unique frequency selectivity. Right? As you sweep across a very broad band, you'll see pattern A has a, if I were to draw it on the screen, pattern A has a frequency selective profile. Pattern B has this frequency selective profile. So in theory, I have two different pieces of metal with different shapes. I should be able to tell them apart electromagnetically. And for the most part, that's true. But in practice, these type of chipless electromagnetic identification structures don't really work unless you're this far away from them. And the reason is, if I make a broad measurement, I send out a wave to measure the frequency selectivity of multiple objects. I cannot tell the difference between the frequency selectivity of the object or the frequency selectivity of the environment because they occur at the exact same time scale, delay scale, and frequency scale. However, if I have a surface acoustic wave device, I introduce an unnatural amount of delay to the return signal. So what does that look like in the time domain? I have a reader that sends out a wave. All the reflections will come back, and then the wave that went into my saw tag into and then out of my saw tag will have arrived much later. So if I looked at the power delay profile that I measure, I see this, a slow decay, nothing below the noise, I'm below the noise limit of my receiver, and then I see a little thing like this. Well, using some signal processing, that becomes very easy to disembed. I just kind of gate my response. I'm going to throw away everything that came up past the threshold, and I'm just going to look at that window in time. This is in the delay domain. If I view this, which of course is measured in units of time, if I view this in frequency, what this looks like is I have an environment like this, but then I also have some fine scale behavior that's very unnatural. It would have a high frequency, very small coherence bandwidth that I can pull out through signal processing as well. Normal things don't behave like this. Normal materials in our physical world do not behave like this. So for that reason, I can use signal processing and pull them out relatively easily. Remember, with modulated backscatter, I don't really have that problem because the object that I'm listening to, a low power piece of electronics that's load modulating antenna, that's introducing time variations. Most normal things don't have time variations to them, so it becomes very easy to pull that out of the clutter. I send out a wave, I get a bunch of unmodulated backscatter coming back, and then a little modulated signal, which is really easy to key off of because it's changing at a megasecond, on the order of a megahertz or something like that. Here, I'm saying I've got saw tags in my field of view, I send out waves, I get a bunch back, the saw tags are static. But it's easy to, unlike the case of just a regular electromagnetic signature of a tag, of a piece of metal, I can pull that very easily out of the environment because they operate at such different time scales and frequency scales. So let's just work a simple example here with some numbers here. I have a saw lithium niobate tag. It's supposed to operate at 433 megahertz. It has 50 pairs of fingers, 50 on one side of the transducer, 50 on the other. And the transducer itself, or the tag itself, is 400 micrometers long. this is the transducer specs. So the transducer is 400 micrometers. What can we glean interesting about this transducer? So here's my transducer. Well, first of all, we already know what the bandwidth is for this thing. The bandwidth is the center frequency, which is 433 megahertz, divided by the number of fingers, 433 times 10 to the 6 hertz, or 1 over seconds, divided by 50, is going to have a bandwidth of about 8 megahertz. And what's more, that 400 micrometer long transducer, that's 400 times 10 to the negative 6 meters, spans 50 pairs of fingers. So finger 1, finger 2, finger 1, finger 2. It alternates across. So there really should be about 100 of these fingers across. And the spacing in between the fingers should be lambda over 2. So this should tell me exactly what lambda should be for this device. So at 433 times 10 to the 6 hertz, 433 megahertz, I get an estimated wavelength of 8 micrometers. Which means now I can get something else information, some other useful information out of this. I can estimate what the velocity of propagation is for the surface acoustic waves. We know what frequency is. We know what the wavelength is. If we multiply them together, we get 3.5 times 10 to the 3rd meters per second. 3,500 meters per second. Much slower than the speed of light. So now let's say I use this material in a sensor. And now I have a saw tag that's 1 centimeter wide. And it's going to be interrogated by a reader that's scanning at 433 megahertz. And that this tag is 100 meters away. So then, what is the maximum transit time for this signal to go from reader to tag and then back to reader? Now I think I've drawn this a little bit misleading here. Let me change this. So the tag, the transducer for this tag, and this is actually based on a sample that I used to pass around to my antennas class. And in this case, it's a 1 centimeter tag, but there's about a ½ centimeter on both sides of the transducer to travel on. So think of this as a 0.5 centimeter tag to get basically from the transducer to the end of the material, where there would be 100% reflection back towards the transducer. So let's figure out the RF transit time. That would be 100 meters divided by 3 times 10 to the 8th meters per second. And I got to do that twice. I got to go, and then I got to come back. And that's going to produce, when I multiply by 2, 667 nanoseconds. The acoustic transit time I am traveling half of a centimeter, 0.005 meters, and I'm doing it at 3.5 times 10 to the third meters per second. And I'm also doing that twice, right? Because I basically, if I look at my diagram, I come into from my antenna to the device, down and back. So I also have to multiply that by 2. What do I get? 2,857 nanoseconds. So despite the fact that the signal in the acoustic medium is only traveling a half a centimeter, if I try to interrogate this tag from 100 meters away, the total transit time, less than 20% of the time is actually RF. It takes me 1/5 the time to go to the antenna and back than it does to actually stay within the acoustic medium, hit reflector bars that encode information, and then come back. So you see why this is a very effective technology for doing some interesting sensing applications without batteries, right? I was on a committee, serving on a committee of a PhD student at Georgia Tech that had made a really neat ozone sensor using surface acoustic wave technology. Theory's not interested in temperature identification. We're not only interested in those, but he found that as ozone or whatever gas you want to sense, you can sensitize the surface of these materials so that their mechanical properties change when certain molecules like ozone, or you're sensing the molecule you want to sense, as they attach to there. And so it changes the velocity of propagation and the reflector bar characteristics. And you can actually look at the electrical return and figure out how much ozone this tag had been exposed to. You could make a dosimeter for an employee that worked at a factory. Or you could have just a bunch of these sensors around your airport sensitized to noxious chemicals that you want to make sure don't show up in the airport. Stop the terrorists, right? Kind of the problem. So there's a lot of really neat things you can do, and we're just kind of starting to understand some of the applications that we can realize by transducing the medium of RF. I think I've already blown past my time, but I just will say one other new area of investigation is bulk acoustic waves, which behave very similarly, except in this case what you do is you put your voltage across the medium and then you excite a bulk wave through the material instead of a surface wave. And then by epitaxial growth you can actually try to make different, you can put spacers in between there of different lengths. So here's your metal, and in between here you have piezoelectrics and a combination of thin films of damping or different velocity of propagation media that causes reflections in the material. And by changing the thicknesses and the composition, you can make a really neat filter response that way. But now you're kind of building up instead of relying on a long surface acoustic wave substrate. There's some advantages of doing it this way. So I think maybe some of these BAW filters have actually made it into your phones and handsets. And I don't know anybody who's built any RFID tags or sensors out of them yet, but there could be some out there by now. It might be an interesting project topic if you wanted to investigate it more. Any questions? No? Okay, let's finish.